Hello, I'd like to welcome you to today's Makino Experience Center. My name is Bill Howard. I'm the product line manager for vertical machining centers here at Makino. Our topic today is Slim3n milling capability. Slim3n is a product that we've just recently introduced, and it's an entry into a new market for us. So I'd like to talk a little bit about that capability and what separates it from the competition. Some housekeeping while we're chatting here. You'll notice on the right-hand upper corner there's a chat Q&A, and there's a box down at the bottom. While we're going through this, if you have any questions, you can type those in, hit send, and hopefully we'll have some time at the end of today's Makino Experience Center to address as many of your questions as we can. So that kind of gives you an idea there. I'm coming to you today from Makino Corporate Headquarters, which is the building on the right in Mason, Ohio, just north of the city of Cincinnati. Actually, in this building, there are two experience centers. We're in Experience Center number 1. There's another one down the hall, Experience Center number 2. In addition, combined with the experience centers, we have a number of machines out here, and we have cameras on the machine so we can bring live cutting action into the room. On the left-hand side of the screen is our Auburn Hills, Michigan facility. That's north of the city of Detroit in Auburn Hills. We have 2 more experience centers there. Now, talking about experience centers, think about the capability this provides us and you. We can put together a focused, directed, so if you want to talk about machine, or if you want to talk about a part, or an application, or tooling, or a turnkey, or automation, your manufacturing needs, we can do that in a confidential setting. And what's really nice about it, it allows us to get our team members and your team members together so you can have more folks involved. You don't have to make decisions as to who can go and who has to stay. And the other thing, it's very, very inexpensive. So there's not a lot of travel, and you're not going to be away from the factory or facility. So I'd like to encourage you, as you see us go through this today, think about how you could use the Makino Experience Centers with our folks and your folks teaming together on your manufacturing needs. Just talk to a Makino representative about setting something up. We're going to go into today's content. And today, like I said, we want to talk about the Slim3n milling capability. Let me get my clicker here, and we're ready to go. The Slim3n is a product that we've just recently introduced. It comes in 2 versions, a standard table version on the right and a pallet changer version on the left. And by definition, traditionally, this fits into a category of machines that will be called drill and tap machines. And I'm sure you've heard drill and tap machines out there. So the Slim3n fits in that category, although we're going to talk about what makes it different in that category today. Well, what's a classic drill and tap machine? You can see right there. It's a machine. Here's kind of a typical part. It's got a lot of holes in it, so you're doing a lot of drilling and tapping. Now, here's a kind of an image or a video of a classic drill and tap machine. So you'll see it comes down, and there it's drilling. And there's a tool change. You'll notice the turret on the front. We'll talk about that. But it's drilling and tapping. So that gives you an idea of the classic application of a drill and tap machine. Now, if you will, come for a walk with me around in your facility. What do your parts look like? Well, the odds are they look something like that, an oil pan, aluminum die cast, but there's a lot more than just drilling and tapping in that part. There's milling, there's bosses. Same thing here, a cylinder head, die cast aluminum, milled surface, drill, tap. So how about there's a crankcase. Again, aluminum die cast, but there's milling, drilling, tapping, boring, clutch housing. All of these are aluminum die cast. What about something like this? It's a disc drive case. That's made from solid. So you got to go in and you got to mill out and make a cover. So that is a part that's probably out there in your facilities, or other type of hog out type parts. Here's a sintered steel part. Again, there's milling, there's drilling, there's tapping, there's bores. So there's a lot more there than drilling and tapping. Well, what about different types of material? Do you cut steel? Look at that part. Yes, there's drilling and tapping on it, but there's milling as well. Here's a cast iron part. Same thing. Drilling, tapping, but milled surfaces. Okay. Here's a forged steel connecting rod. Drilling, tapping, milling. How about a forged steel hydraulic manifold? A lot of drilling, a lot of tapping, form cutters for fittings. But, you know, it's a lot more than just drilling and tapping. Another crankcase, cast iron. And in today, what about medical applications? Things like stainless steel, titanium, cobalt chrome, even plastic wear parts. So on that walk through your shop, I think we found a whole lot of parts. Yes, they've got drilled and tap holes, but they've got a whole lot of other machining as well. So the questions become, do your parts require more than just drilling and tapping? And I'm going to bet that in a lot of cases, you're going to say, yes, they do. Well, then if they do, why invest in a machine to just drill and tap? If you think about it, you're increasing your cost. You're increasing it by the capital expenditure on the drill and tap machine. You're increasing it by handling the part more often. You got to get it on and off the drill and tap machine. That's handling. You got additional labor to do that. You've got inventory, work in process. I'm going to have to stack up parts in front of that drill and tap machine, and obviously after the drill and tap machine. I'm also, by virtue of that, going to have a longer throughput time. I've got more steps in the process, more work in process inventory. So I have a more complex manufacturing process, and all of this is going to increase the cost of my final manufactured part. Well, that's the focus of today's Experience Center. Let's go in and take a look. And I brought some demo in here. We're going to talk about HSK A50 and a CAT 30. So here's almost all of the competition is exclusively a CAT 30 spindle. The Slim3n Makino is an HSK A50. So when you look at a chart and you circle them, there's most of the competition, CAT 30. Here is the Slim3n HSK A50. Well, you look at that chart and it says, you know, gee, it's a push. They're both at the same level. Well, let's be an engineer for a minute here, and let's go in and take a look. Let's look at the CAT 30. Here's your CAT 30. Let's take a look at the HSK A50. One of the first things you're going to notice, the small end diameter. On a CAT 30, you're looking at about 32 millimeter diameter, okay? On an HSK, you're at 38. So it's a bigger diameter. You might say, well, gee, is that important? Well, think about where is the interface between my spindle and the cutting tool? Well, it's with that small diameter. So I've got a larger surface to grip on the HSK than I do on the CAT 30. The other thing is the big end. It's 50 on a HSK A50, obviously, and it's 46 on a CAT 30. So the bottom line here is I have a 20% larger diameter on what I'm going to call the machine tool working end of the tool versus over there. And I've got a 10% larger diameter on the machine tool, on the cutting side, the work zone side of the tool. Now, which of those do you think, larger diameter, which of those do you think is going to give you a better grip on the tool? The other thing we're going to talk about here a little bit, you'll notice the difference between the 50 millimeter diameter and the 38 is 12 millimeter on a diameter. So there's about a 6 millimeter per side or 6 millimeter circle there, but on the HSK A50 that you do not have on the Cat 30. And we'll talk about what that's used for here in a second. Now you think about manufacturing for a cat holder. Well, first off, you got the spindle. And in the spindle, you're going to have some allowable tolerance for the taper. So that's shaded in yellow. On the tool itself, you're going to have some allowable tolerance for the taper of the tool. So consequently, there's a perfect taper there. Unfortunately, different spindles and different tools are going to be somewhere in that allowable tolerance band, and therefore that's going to impact how the tool fits into the spindle. And again, almost all the competition is exclusively Cat 30. The other thing is there's a space between the spindle and the holder at the end. Now, why do you think that would be? If you think about, the tolerance built into the spindle and then the tolerance built into the tool, obviously as you seat that tool, sometimes it's going to seat up in here, sometimes down in here. So the tool's going to go up and down in here. So you need some ability to pull the tool all the way up to where it seats up here or when it seats down here. So that's part of the allowance, if you will, for a Cat 30 type design. There's that gap or space between the tool holder and the spindle. Now, here you can see it's seated all the way up in here. In another case, it could be seated down there. The other thing about it, what if it's kind of seated, obviously this is an extreme example, but more like on an angle kind of thing. So it's all dependent upon where it seats against the spindle. Well, as you'll notice, what happens is up here is where you've got contact, down here is where you're trying to measure run out, and every time this rotates, you're going to get some run out. Well, is that good or bad? Well, you can see here, your tool life impact as a result of TIR, or total indicator reading, and also over here, this specifically is for drilled holes. And you'll notice, depending on the TIR, you could go from, say, 140 all the way down to 70. So you could have a change of 50% in the number of holes you could drill given the TIR. So very important. Let's talk a little bit more. As I said, first off, drawbar force on a Cat 30, about 1,200 pounds. Drawbar force on an HSK A50 is about 2,500 pounds. So there's twice as much drawbar force on the HSK. So if you look at this, I've got twice as much force on the HSK as I do on the Cat. Okay, the other thing is, let's talk about technique. What I'm trying to do, you look at the red arrows there, I'm trying to grab this knob and pull up with 1,200 pounds until I seat somewhere on this taper with the tolerance of the spindle and the tolerance of the tool. So that's the design. And you can see how it could go like this. Here, I'm reaching down inside here, grabbing, expanding, pulling up. So I'm seating on the outside. Plus, you remember those little red pads we talked about? There's a face seal where we will pull this right up against the nose of the spindle. So that's a major difference in the designs of the cat and the HSK. Remember we talked about this little 50 millimeter, 38 millimeter, we got 12 millimeters there. So about a 6 millimeter per side or diameter around there. What's that mean? What that means is with the cat, we talked about the gap and the reason for the gap, allow it to seat. With the HSK, we're actually pulling that up so that we've got a solid side relationship with the back of the HSK holder. So what's that going to do? It's going to be very stiff, very rigid. It's going to impart the stiffness and rigidity of the spindle into the tool. And obviously, it's going to have a very big impact upon spindle runout. Here's a classic example. This is a cat. Low connectivity, you one point, one face, bad tool change repeatability, and you have low tool holding security, if you will. And the other thing is you tend to have much more run out. Now, let's look again here at the HSK. And the HSK, we already talked about, typically HSK has a much higher retention force. So more stiffness, more rigidity. It has less deflection, as you can see here, for given load, less deflection. And that's, again, the face mounting and the fact that you don't have that gap and you're not seated at various different positions up in the Cat 30 taper. And then last but not least, you have much higher torque transmission capability with the HSK than you do the Cat. So all of those, I would argue, are very positive things as a result of a HSK holder versus a Cat 30 holder. Now here's the HSK example. You see how we grip out, seal here, face there. So high connection, rigidity, good tool change, repeatability, extremely good, and very low run out, very good high speed performance. So that's kind of a, if you will, design sharing between a Cat 30 and an HSK 63. In summary, HSK is two faces, the spindle nose and the taper, whereas the Cat is one. So very good connection, rigidity, stiffness. Tool change repeatability, much better here than there. Tool holding security, much higher with an HSK than the Cat. High-speed applications, this is the best application, obviously, for run-out, stiffness, rigidity versus the Cat. And obviously run-out, again, very low run-out here, very high run-out for the Cat design. Again, in kind of a looking, what's the impact? Well, what we're looking at here is tool life. You'll notice Cat, BT, SK, they're all up in here because of the run out and that how it affects tool life. So let's pick this number here, which is 40 on tool life. Well, the HSKs tend to have less, more stiffness, more rigidity, less vibration. I mean, here's a number of 160. So we could go from 160 to 40. That's what? 4 times. 4 times the tool life capability on the HSK holder versus a Cat or BT type holder. Let's go in and look a little bit of the technology behind the Slim3n versus the competition. As you can see, we use a 55 millimeter, 2.16 inch diameter spindle bearing. The competition is around 30 to 32, 35. So if you think about it, cutting, you're applying a force at a distance from the spindle and obviously the bearing. So here's the smaller bearing, the larger bearing. And what you're looking for is deflection. Which spindle is going to have the least amount of deflection? Why is that important? Well, obviously run out, cutting capability. If the tool's trying to deflect because there's no stiffness or rigidity in the system, you're going to get a lot of this, which is chatter, and a very bad tool life, very bad surface finish. There's three types of loading on a spindle bearing. The first one over here is radial load. That's typical of your tool, and we're down here cutting, so you got a side load typical of milling. You have axial load. That's typical of drilling. I'm going to go down here and the force is going to, so that's an axial load. And then you have moment loading, which is typical of milling. So I'm going to mill and I'm going to be cutting down here. So I'm trying to turn or overturn the spindle. I'm generating moment. So those are the three loads we got to kind of think about and how we design the machine. And if you think about the very beginning, we said classic drill and tap machines. Well, if you were a drill and tap machine manufacturer, where would your focus be? Well, your focus would be on drilling and tapping, axial loads. What about milling at a length L with a force F at a distance from the gauge line? Well, that's going to generate radial side load and moment. Well, let's go in and let's take, this is a bearing booklet table. Let's pick a class of bearing, typical of spindle, and let's take a look at two different sizes. Let's take a look at a 55 millimeter diameter, and let's take a look at a 30 millimeter diameter. Well, one thing you'll notice right away, there's a difference obviously in diameter. That difference is 55 minus 30, which is 25 millimeter. What that means is I can get an 83% larger shaft or spindle in that bearing versus this bearing. So there's what that would look like. What's that mean to you for stiffness, rigidity? Obviously, the larger bearing is going to have higher stiffness and rigidity. Now, let's go into that same table, and for these two diameters, pick some stats. C dynamic is the radial load, so that's the radial load capability for the bearing. On a 30 millimeter, same class, same manufacturer, same type, same materials. So it's basically 1-to-1 except for diameter. You're looking at about 1,000 to 5,400 pounds of dynamic load capability, so the average is about 3197. On the 55 millimeter, you're looking at almost, 2,100? Your high end is 12,400, so the average is 72. So you've got 2.28 times more dynamic radial load carrying capability on that 55 millimeter bearing than you do with 30. So keep that in mind. Okay. Another thing to think about, we talked about earlier that a cutting force at a distance generates a moment. So what I've got here is a little chart for the small bearing and the large bearing where I've taken the radial load carrying capability and I've multiplied it by tool length. So you'll see there, and this is in inch pounds. So, and you'll notice some gray there at the end. The gray there at the end is for a number of reasons. One of them, if you saw that in the beginning, the tool magazine on virtually all of the competitive machines is a turret. And so therefore, there is a limit as to your Z-axis and your workpiece size and how long a tool you can have. So most of the competitive machines, you can't get much longer than about a 10 plus a little bit tool. So that's why there's gray there at the end, whereas the Slim, you can go up to a 12-inch long tool. What happens when you have a tool length with a load at the end of it? Well, obviously you generate, as a result of the cutting force, you generate a moment. And here in blue, and that's what we're talking about. Here in blue is for the smaller bearing, and in gold is for the larger bearing. Now here's the gray area where the machine won't handle a tool larger than that, so that kind of ends that situation. But here's the advantage of a larger diameter bearing. Obviously you can have, cutting force at a longer distance and not overpower the moment of the bearing capability. It's a classic cantilever beam type engineering question. I've got a given force at a given distance. What's the deflection? Well, it depends on the cross-section of the beam. So here we've got a little video, and it's going to talk about the CAT versus the HSK, and here's the diametrical difference. So you can look at this two ways. How much force does it take to generate the same amount of deflection? Or, what force give me the same deflection? And what you find is the answer is 12-1. So if I'm looking for how much can I get with the same deflection, it'd take 12 times the force, or, to get the same deflection, I could have 12 times the force and get the same deflection. So that gives you an idea of the capability of the HSK and the diameter versus the CAT. Now, talk a little bit about perishable tooling and machine design. This is kind of a side benefit, but if you think about the Slim3n, very stiff, very rigid, the table is fixed. We're moving all the axes relative to the workpiece. So very good stiffness, rigidity, axe dex, high speed, none of that is impacted by part weight. So accuracy, the ability to automate. So we need to remember that heavier, stiffer structure. Most of the competitive machines are a C-frame, so you're aware of the capability there with X on top of Y and then Z. And then the other thing is oversized linear guides. The Slim3n typically are significantly larger, stiffer, more rigid, so good cutting capability. So the machine is built as a milling machine that just so happens to be able to drill and tap. And then we've been talking about the bearings. We went out and kind of took a look, and if you talk to the tooling vendors, they say, a typical machine anywhere from $25,000 to $50,000 a year in perishable tooling. Well, you can see here that we've got about a 20% longer machining time to reach a certain flank wear on that perishable tooling. What does that mean? Well, let's just take the low end number, $25,000 a year in perishable tooling times a 20% benefit. That's $5,000 a year. Well, that's savings to you, year in, year out. 10 years, you're looking at 50 grand. The average life of a machine tool today, 15 years or more, you're looking at $75,000 to $100,000 that you have saved while manufacturing your componentry. Let's take a look at spindle characteristics. Look at it, horsepower here for standard spindles. There's the Makino Slim3n in the blue, 20 horsepower, 16,000 RPM. There's one of the competitive machines, and there's another competitive. Both of them are 10,000 standard. Now, interesting to notice, there's now a thing coming about called maximum horsepower. What does that mean? Well, it's a point where the machine gets its maximum horsepower. You'll notice it is the one and only point on the power curve. So from 0 to that point, it's constantly changing. From that point out, it's constantly changing. And you don't get that until you're all the way out about 5,000 RPM on a 10,000 RPM spindle. So it's specsmanship, if you will. Our machine's 20 horsepower. From here to here, we achieve it at 4,000 RPM. Well, they don't achieve, number one, theirs is 25 horsepower. So 25 is better than 20, right? But you only get it at one point, and you don't get it till 5,000 RPM. So that's a thing to watch for as you look at spec books. Here's the optional spindles. Makino offers a high torque 8,000 RPM on the Slim3n. The competition has a 12,000. They have a 16,000. They have a 10,000 high torque. And then there's a 24,000. And again, you'll notice there's a lot of use of this maximum horsepower. You notice on their 12,000 RPM spindle, it doesn't get maximum horsepower to 6,000. On the 16,000, it doesn't get it till 8,000. And again, it's constantly changing up and down. Look at torque. There's the Makino torque curve in blue. We're about a 26, 27 foot-pounds. Here's the competition. Again, they're at 30. So 30 is better than 26, 27, right? Well, and then here's the other competition. You'll notice again a kind of a new term. It's called momentarily maximum torque. So you'll notice the maximum torque is 30, which is higher than 27. But by the time you get out to 2,000 RPM, the advantage is clearly the Makino. Now, what if you had a tool that you needed to adjust RPM in order to get best cutting conditions? You have, with momentary maximum torque, you're very limited. And here's the same thing for the optional spindles. There's the Makino 8,000 high torque, 60 foot-pounds. There's the competition. Another competition at 8,000, 10,000, 16,000, and 24,000. And again, you'll see the use of this momentary maximum torque. So the good news is, if you're a specsman, that's 67 versus 60, so that's better. But again, by the time you get out around 2,000 RPM, that advantage is going away. So very little adjustability for RPM on the torque curve. What we're going to show you is a demo here. We're going to start with a solid block of aluminum. We have 2 ops, and we're going to end up with a little business card holder. The 2.1 pounds of aluminum to start. The finished part's 0.55 pounds. So we take away 1.55 pounds, or 74% of the block, in about 7 minutes and 39 seconds. This is not your classic drill and tap machine part, and you'll see why here in a minute. First off, we use a face mill. It's about 4 3/4, 120 millimeters, 4 3/4 long, about 80 millimeter diameter, 3.15 inches. Okay. At the end of that tool, about 4.73 inches is 80 foot-pounds. So we're generating about 380 inch-pounds of moment into the bearings. And remember, we talked about that in larger bearing, higher stiffness and rigidity, and also about the impact of tool length and the advantage of moment capability in that. So here's a real quick video, and I apologize, there's a lot of, but you can hear it. It sounds like a milling machine. Okay, so there was that face mill cut. We're doing about 42, 43 cubic inches of metal removal per minute. Now, let's go in. There's what that cut took in horsepower and RPM. Here's one of the competitive machines. Well, gee, we've got a problem. You couldn't do that cut on this machine. You'd have to, well, no matter how far down you slid, you'd never get enough horsepower. And furthermore, sliding down that RPM curve in order to get power is non-productive. You're slowing your cycle times down. So the other thing, obviously, we're running at 8,900, almost 9,000 RPM. Those 2 machines both tap out at 10,000. So if I had to adjust this way, I've got very little capability to make any adjustments that direction. Here's the torque curves. There's the torque of that cut. 9.6 foot-pounds at 8,900 RPM. Well, again, one of those machines will not make that cut at those stats, so it'd have to come back this way, which that's productivity, cycle time. The other machine, you'll notice, it's one of those instantaneous torque machines. By the time we get down here, we're taking almost 10, and that's 10 right there. So you're pushing the machine right up to the limits, and both 10,000 RPM, whereas the Makino goes up to 16. So you have a lot of adjustability and capability in that cut. Here's another cut. This one happens to be about 169 millimeter long, 20 millimeter diameter. So there's 6 3/4 inches, 6 2/3 inches rather, and it's an end mill. So again, at that distance, 150 pounds, which generates right around 1,000 inch-pounds of moment. Again, don't forget the bearing size, stiffness and rigidity, and we're getting out in here 7 inches. We're out in this area, whereas they're here. So here's that cut. Keep in mind, I apologize, a lot of coolant in this, but look at the length of cut engagement on the tool. So here we go. A milling machine sounds like it. Again, we're taking about 18.5 cubic inches of metal per minute. Let's go in and do the same kind of analysis. 9,000 RPM, 8.1 horsepower. Well, again, we got a machine here that we're going to have to back way off in order to be able to make that part. And the problem there is once you back off, cycle time. So good news is I can make the part. Bad news is it's going to cost me a lot more money. Here's the torque curve. Torque-wise, everybody's kind of okay. We're down here at 4.7. This guy's got 7. This guy's got 9. We're at 11. So we're comfortably. And the other thing is if we had to adjust for RPM, they're out of RPM at 10. We've got all the way out to 16. The thing that bothers me more about this cut is not so much, the torque. The power, obviously, on one of those machines, but the torque. The thing you got to consider here is the length of tool. You're 6.6 inches hung out the end of that holder on this cat like this, which is being held like this. And so you're way down here. And what's that tool going to look like? So we talked earlier about tool change and, the carousel or as you get into this, one of the things about spindle impact and spindle design, if you look at tool diameter, the Slim3n can handle much larger diameters than the competition. I contend that part of that's limited because of the robustness of the spindle. If you can limit the diameter of the tool, you can limit the moment that you can generate on the tool and the spindle. Same thing with tool length. You look, most of the competition, almost all the competition, tool lengths are limited. Part of that's the design of the turret on the front of the machine, but part of that is if I get a real long tool and I get a cutting force on the side, my moment's going to go way up, and my radial force and my moment on the bearings, and it's a drilling and tapping machine. They weren't built to do that kind of thing. So there's another. And then tool weight capacity. Couple things here. Just trying to hold that weight up the way you do it with the Cat 30 holder. The other thing is inertia, mass. You start getting heavier tools, you're running 10,000, 12,000, 24,000 RPM. Takes a long time to slow that spindle down, get that spindle back up to speed. So these are real limits to the size, length, diameter, weight, capability of tooling you can use on the machine. All of these limit your machine productivity. And they're not necessarily there as a result of the machine design. They're there as a result of the spindle design and the impact of the spindle upon what I can handle on tool length, tool diameter, and tool weight. That concludes the formal presentation today. And at this point in time, I'd like to throw it open to try and answer some of the questions.
There were two basic questions that came in. Try to address those. One of them, and today we focus primarily on cutting capability and basically showing that, the Slim3n is a milling machine that just happens to be really good at drilling and tapping. The question was about parasitic times. And if you remember back to the slide about the table on the Slim doesn't move, X, Y, Z moves around the workpiece. So consequently, we tend to have much higher rapid traverse rates and ack and deck rates because we're not having to worry about the weight of the part or the fixturing or anything. So therefore, the parasitic times tend to be less, which means you're going to have a quicker cycle time. The other thing that the question came up was about control. And it kind of falls into two camps here. On the Slim3n, we use a FANUC OIMF control, one of the most popular controls in the market today. Obviously, one of the competitors would be a FANUC. Another competitor has their own control. It's a CNCA00 is what they call it. So those are kind of the questions that come in. I don't see any. Let me check one more time. Don't see any other questions right now. So I'd like to take this opportunity to thank you for joining us for today's Experience Center about the Slim3n milling capability. In fact, it is a milling machine that just happens to drill and tap really well as well. I'd like to also remind you that if you registered for this Experience Center, you should be getting an email which will have a link that will allow you. So if you have other folks in your organization that you think ought to take a look at this, you can share that link with them. And in a couple days, we'll be posting this to the Makino archive. You can go there to www.makino.com and take a look at the webinar archive. So once again, thank you very much for joining us today.